Okay, so you might have seen this video that's been making the rounds for years. It's a cosmonaut floating in zero G, and he just gently spins a T handle, kind of like a wingnut. It starts out spinning perfectly fine, and then it just flips over, out of nowhere. Then it spins a little more and flips again, with this really weird, regular rhythm. And believe it or not, that simple little flip is forcing us to completely rethink our understanding of time itself. You know, when that footage first got out, people went wild with theories. They called it all sorts of things: space voodoo, a glitch in the matrix, you name it. But what if the answer isn't weird at all? What if it's actually something way more profound, like a hidden clock ticking away inside the very shape of things? And here's the thing. This isn't some far-out phenomenon that only happens up in orbit. This so-called cosmic glitch, which has the official name the Johnny Bekoff effect, is something you can actually see for yourself right here on Earth. No, seriously, give it a try. Grab a book, a rectangular one works best, or even your phone. If you toss it spinning along its longest axis, end over end, the spin is totally stable. Same thing if you spin it along its thinnest axis. But try to spin it around that middle axis, that in-between dimension. It will, without fail, flip over on you. Every single time. Yeah, there's actually a name for this, the Tennis Raquet Theorem. And for well over a century, scientists and mathematicians have known that spinning an object this way is just unstable. The flip is basically guaranteed. But knowing that it's going to flip is a whole different ballgame from understanding why it flips with such a perfect, predictable beat. And that's where the classic explanation kind of hits a wall. It tells us the middle axis is unstable, sure, but it has absolutely no answer for the clockwork regularity of the flip. Let's dig into what that really means. So on one side, you have totally stable, predictable motion. That's what our brains expect, right? A smooth, clean spin. But with that unstable rotation, it's like the object is storing up some kind of tension, building something up until it just has to release it with a flip. Now, the old school math, and we're talking about equations that go all the way back to the 18th century physicist Leonhard Euler, it totally confirms this instability. It basically says that any tiny microscopic wobble will get bigger and bigger until eventually it forces the object to tumble over. It explains that flipping is possible. But here it is, the million-dollar question. If the flip is just caused by some random disturbance that spirals out of control, then why isn't the flip itself random? Why does that wingnut in space flip, spin for a bit, and then flip back again, almost like it's counting? The old theory? It's got nothing. No answer for that. And this is where a really fascinating new theory enters the picture. It suggests that the flip isn't a mistake. It's not a failure of stability at all. No, it's the ticking of a hidden clock, one that's literally built into the object's geometry. And to really get our heads around this, let's use a super simple analogy, one that you'll definitely remember from the schoolyard. Okay, picture it. Two kids are swinging a jump rope, and you're standing on the outside, right? You're kind of rocking back and forth, you're feeling the rhythm of the rope. That internal timing you're building up, that's called a phase mismatch. You're a little out of sync with the rope, but you're learning its beat. You can't just jump in whenever you feel like it. You have to wait for that perfect moment, and then you jump. Well, that spinning racket, it's just like you, waiting outside the rope. With every single rotation, it's accumulating a tiny little mismatch. The flip isn't some random error, it's the racket finally jumping in to get back in sync with itself. So to put it a little more scientifically, this new theory says that because of its uneven shape, the object builds up this tiny time drift with every spin. It's like a clock inside the object is ticking just a fraction of a second off from the outside world. And when that tiny drift adds up to a certain point, bam, the flip happens and the clock resets. Okay, this is where it gets really, truly wild. This whole thing, this modern physics puzzle, this spinning glitch, it turns out it's deeply, fundamentally connected to a mathematical crisis that went down in ancient Greece. Just look at this timeline. Over 2,000 years ago, you had the Pythagoreans, who believed the entire universe was built on beautiful, perfect whole number ratios. Then this guy Hippasus comes along and proves that something as simple as the diagonal of a square, the square root of 2, is an irrational number. It can never be written as a perfect fraction. It completely shattered their worldview. And it's that exact same mathematical incompleteness that we're now using to explain why the wingnut flips. What this really means is that the geometric imbalance in the tennis racket creates a kind of physical, real-world irrational number. Every rotation adds a little bit of what you could call time debt that never quite resolves perfectly, just like an irrational numbers decimal goes on forever without repeating. The flip, that's just the universe's way of paying off that leftover debt. So what does this all add up to? It means we've been looking at this thing completely wrong. The flip isn't a bug, it isn't instability or chaos, it's a feature. It's a sign that geometry itself keeps time. And this new way of looking at it is incredibly powerful. For starters, it finally explains the regular timing. It shows us the flip is just a release valve. And get this principle doesn't just apply to tennis rackets. It applies to quantum particles, to fluid dynamics, even to the way our own inner ears sense rotation. And best of all, it makes a prediction that we can actually test. If you build a perfect mirror image of an object, the timing of its flip should change in a very specific way. One of the papers that inspired this explainer puts it perfectly. Time doesn't just flow, it records. This theory suggests that as an object tumbles through space, its own shape is leaving a mark, a record of its own journey, stored as this tiny little time drift. So that's the big takeaway here. What looks like a chaotic failure of stability, that flipping wingnut in space, isn't chaos at all. It's a beautiful, elegant, hidden rhythm. It's the sound of geometry counting. And every so often, just turning the page. Which really leaves you with a final, fascinating thought. If a simple, spinning object has a secret clock ticking inside it, a clock that connects all the way back to the mathematical discoveries of ancient Greece, what other perfect hidden beats are woven into the fabric of our universe, just waiting for us to find them?